I would like to give you a feeling about electrochemistry. So what are the fundamental processes behind? So we speak about metals and semiconductors, mainly metal electrolyte interface and semiconductor electrolyte interface. So from fundamentals to kind of applications, so what you can do with it. So if we speak about electrochemistry, we just study electrons, how they move from high chemical potential to low chemical potential. So it's a bit like a waterfall. It's a classical image for electrochemistry. So you can imagine if an electron is high up the mountain, so it really wants to go down because it's much more quiet down there. So let's say the electric potential difference is determined by the height of the waterfall. And it's the same with electrons, it's determined by the voltage difference. So in this actually you can convert also kind of Ohm's law, because in this case the water falling down is the current. So they have a high potential difference and the current flows to high energy to low energy. And of course, this process is spontaneous, as you see. So it's a natural phenomenon. Everything which goes from high to low energy can be spontaneous. But it can also, so this would be the principle of a galvanic cell. So we take two redox couples with different Fermi energies. And this difference in redox potential is the driving force for the current to flow. But you can also have a case where it's not spontaneous. So it's like you put a pump down on the waterfall to pump back up the water. And in this case, you keep the current flowing by an applied potential. So you force the system out of equilibrium. So now we start with the discovery of the spontaneous reaction, so the galvanic cell. And actually it's not very long ago, it's only a few hundred years. So 10 generations or a little bit more. So it's not too much. So Luigi Galvani, 1780. So they were very interested in electricity, so they thought they need animals to have some electricity. So they had two electrodes, one copper, one zinc, and they put it on the frog leg of the frog. And suddenly they saw it reacting. So and this, they called it animal electricity. So it's a very particular phenomenon. And Alessandro Volta, so Italian friend, he didn't believe the story. He thought it's not possible. There must be a kind of electrolyte in the leg of the frog. So to disprove Galvani, he basically built the first battery. So it consists of copper and zinc plates, and in between you have a kind of a fabric with salty water, maybe seawater even. And he stacked, and he proved that this one generates electricity. I don't know how they measured it exactly at the time, but they were able to measure electricity. So this is actually the birth of electrochemistry, or electrophysiology, electromagnetism, battery research, 1780. So it's all about relative potentials, let's say. And then there's always the question, relative to what? So that's always the question. And if you do electronics, so you have a voltmeter, or a plug here in the wall, it's always grounded. So in the ground, in this case, is your zero level. So it's relative to the ground level. But if you want to do electrochemistry, or in this case in a galvanic cell, basically it's a relative difference between two metals, let's say. If we remember the zinc and the copper, we just measure the relative difference on electrochemistry between the two half reactions, let's say. There's a potential difference. So this you can also measure. But on the other hand, so this is an example of a neuron, you can also measure, so if you have a probing electrode, so it's like a working electrode, so you really want to probe what's going on there, like a pH meter, let's say. And you put the probe inside the neuron, in the axon, and then outside of the axon you have your reference. So this thing is always changing with respect to a known reference, so you can really be accurate to know what's going on there. And then you can see the difference between a rest potential and activation potential. So this is how they can see that everything you think, it's already inside your neurons some milliseconds before you decide to do it. So this concept of free will is made by this. So it's quite interesting. So if we now go do a simple kitchen experiment, we have two, so we have some joules, platinum or gold, and we take the platinum as a reference, so a very noble metal, and we put it on a voltmeter. So we connect them, we have some kitchen salt, sodium chloride, and we see a potential difference suddenly. So gold is a little bit less positive than platinum. It's more negative. Copper, even more, iron, and then zinc has even almost a 1 volt difference. So there is some kind of strange thing which you see. So there is certainly a trend, so depending on the reactivity of the metal. And to understand this better, we have to think in terms of work function. So this is what they do in physics. So imagine you are an electron in a well, very deep down, and you don't want to go out, you're very comfortable there, very low energy. So if you want to go out, it costs a certain energy. And that's related to the different, that's called the work function. So to take an electron from the very low energy, let's say, you take it out and put it at infinity. So infinity is, I don't know, maybe a few centimeters away from the surface. That it doesn't feel the interaction of the surface anymore. So normally if you take an electron out of a metal, you have a positive charge. And this one is attracting each other. So this you have to overcome. And this is, so basically the Fermi level, in this case, of the metal, is the highest energy of the valence electron, of the bonding electrons. So you can then go to the handbook of chemistry and physics, and you can really check different, so we had our jewelry, let's say, you can check the different work functions. So you can see gold has a very high work function compared to zinc, but platinum even is higher. But we should realize that the work function, in this case, is not really a bulk property. It's more like a surface property. Because what you see, for example, you have here different crystal planes. So 100, 110, and 111. So normally in a 111 surface, an atom has 3 backbones. So you can imagine, naively, let's say, it's blocked in the lattice by 3 backbones. So it's more stable. So and this one normally has a higher work function, for example. In this case, it's not the case, actually. And so there's a good question why that is. But what I want to say is that surface has an impact. So even if you have a little bit of oxide contamination, it will also impact the work function. So if you want to measure this accurately, work functions, you have to clean it. So you have to do it in ultra-high vacuum, and you have to sputter the surface to remove all the contamination, and then you can measure. And then hope that your sputter doesn't damage the surface, because then it's no longer an accurate measurement. So it's quite a difficult way. But the most important thing is that we see a trend in work functions. So if we now have our kitchen experiment here on the top, so we see that the potential gets more negative towards zinc, and actually for the work function we see the opposite trend, you see? So the work function is getting smaller and smaller. So that means that a smaller work function metal has a Fermi level quite high, so it's easier to take the electrons out, so the well is less deep. Compared to a more very stable metal, like a noble metal, it really wants to stay in the reduced form. So you need more energy to take the electron out. If you now do, again, you put all the data together, and you put the work functions, you compare it to the reference of platinum. So we have platinum 5.6 versus platinum, so a 0 difference, let's say, and do it also for the rest, and you plot it, then you see that the work function doesn't correlate. There's a trend, but it doesn't correlate perfectly. So one of the issues is if you put it in solution, you have charges on the surface, so you get oriented dipole layer on the interface. I will show that in the next hour. You can see that in more detail. And then you have like an electric field at the interface. Then you have to take the electron through this electric field. So your work function is affected in solution. So, but anyway, the trend is clear. Not a perfect one-to-one. So yeah, you have complex formation. So you have to bring an oxidized metal in solution, costs also energy. So there is a lot of differences here. But anyway, the trend remains quite well. So in physics, they used work functions. Electrochemists used the electrochemical series, metals in water. And basically, the equilibrium potentials, the U0, or the Fermi, or the redox potential, standard reduction potential, or equilibrium potential. So there are many words, so it's quite confusing, all these names. But if you just, I think for me it's easier to think in Fermi level. I'll also show you for the galvanic cell, because it gets much more intuitive to work with this kind of things. So you see that noble metals have a very high positive standard reduction potential, so they really want to take up electrons. So there's oxidizing agents, strong oxidizers, and on the below you have the very reactive metals. So you all know this. These metals, they don't like, they have a very low work function. They prefer to give the electrons away to another system nearby to reduce that energy. And everything is given in the standard conditions: activity 1 molar, partial pressures of 1 bar, a temperature of 25 degrees. Actually, it's a bit warm for a standard. I would say 20. It's more realistic for the lab. But so all about energy difference. So if we now want to make a galvanic cell, so we take two metals, one with a high work function, one with a low work function. It's like this cylinders of water is the same principle. So you have a high electron potential energy on the left, and one with a low potential energy. So what will happen is now if you open the tap, the current starts to flow. In this case, our case is electrons, in this case is the water. In the end, you go to an equilibrium. And then your system stops, your battery is, let's say, dead, equilibrium is reached. So this is the principle of a galvanic cell. On the right, so this is in my street at home, there's a Belgian water tower, and they also use the principle of communicating vessels. So in the past, there's no operational anymore, luckily. They pump it full of water, and this thing that pushes, so if people open the tap, water level push everything to the houses in the street. It's a bit the same thing. But this is like an applied potential system. You apply a voltage, because to keep the water in, they have to pump it up all the time. So it costs a lot of energy, it's quite complicated, let's say. But that's the principle of an electrochemical cell. So you have to put energy in to keep it out of equilibrium. So it's all about energy difference. So the energy and the potential are related through the charge of the particle. So E is Q times U. It's a bit like potential energy. So you have gravity, you take up a heavy stone, you put it against the field, and you put it into a high condition of potential energy, you let it go, it's transformed to kinetic energy. So this is a bit the same thing for an electron. If you put it against a field, so again against the field, it costs also energy to put it in a higher potential energy state. But for electrochemistry, if you do electrochemistry, it's more convenient not to speak in joule. My energy is in joule. It is too complicated. So what you always do, you speak in electron volts. And electron volts is the energy you need to put one electron to a field of 1 volt. So it's 1.6 e minus 19 joule is equal to 1 electron volt. And this is very convenient. I will show you examples of that. So we speak about potential differences. So how can we get energy outside of the system? How can we make a lamp go on? So what we can do, we take two metals. So one metal with a low electron energy, so a high work function, so a very low Fermi level, and we take a metal with a high electron energy, high Fermi level. Sorry, I'm a bit tired. So this metal, lower electron energy, so low Fermi level, wants to be reduced. So it's more stable than the zinc, which want to release the electrons. So basically, what you can see here in the next slide, copper is a stronger electron acceptor than zinc 2+. So copper ions, stronger electron acceptor than zinc 2+ ions. So the noble metals are more positive than the reactive metals, which are negative. So basically, by combining these two half cells, to put them together as a half cell, you can generate electricity. Okay. So this is what it looks like. So difference in metal work function is a driving force. So we have two different electron energies, and the zinc wants to release the electrons to the copper. And in this case, you do a separation of the two half reactions. Because if you don't separate them, they will react instantly. So what you want to do is to delay the reaction. So you put in the middle here a salt bridge. It can be anything. I use a simple glass frit myself. So you block the flow of your copper ions to the other side, but not proton flow. Because when you have such a system, of course you cannot put all the charge to the other side, because you start to charge, you have no charge balance. So what you need to have is an anion or cation flow from one side to the other to compensate. So you always need to have charge neutrality. So in this case, copper is oxidizing agent, so it has a low Fermi energy, so the electrons want to go down, like in the waterfall, and zinc is the reducing energy. So if you combine two metals with different work functions, you can make a galvanic cell. Let's see. Yeah, and basically if you put a lamp in the middle, because you have like an electric field, which drives the electrons, gives the electrons like a speed, kinetic energy, and if you put a resistance in the middle, you slow them down, and then you transform this energy into light, in this case. So if you want to understand better galvanic cells, how they work, so I already spoke a little bit about Fermi level energies, difference in Fermi level energies. It's a very useful tool for electrochemists, or everyone who does solid state chemistry, the principle of a band energy diagram. So as you probably know, electrons in solids are localized in a band. And these bands, you can naively or simplistically understand by considering orbitals. So when you put two orbitals together, you get a bonding state, anti-bonding state. If you now have a metal, it's like 1 mole of atoms, so it's like an infinite number of atoms, you get a very large number of valence band or bonding orbitals and a very large number of anti-bonding orbitals. And the point of the metal is that the Fermi level is localized in the band. The band is not completely full. So this is why the metal conducts electricity so well, because you just have to excite it a little bit, a fraction of thermal energy, and it has a free orbital and it can move in an electric field. So it has plenty of space to move. So it's not like you're queuing, for example. If now I walk out, it's very easy, but if there's a queue, I cannot pass. It's a bit the same simple mechanism. If you now have a semiconductor, it's different. Fermi level is of the so the Fermi level is, let's say, the equilibrium potential of the electrons, and the distribution of the electrons around the Fermi level is given by Fermi Dirac statistics. So, and the statistics tells you that you have 50% chance to find the electron at the Fermi level at 0K, 0 Kelvin. And above the Fermi level, it will go down rapidly to 0. So you have no chance to find the electron there. But in the bonding electrons, so in the bonds, so in the valence band, where all the bonding electrons are, certainly your probability goes to 1 if you go below the Fermi level. So all the bonding electrons are where they should be to keep the stuff together. If we now go to a semiconductor, it's different because now, maybe this was not perfectly drawn, but here the band is completely full in this case for a Fermi level. So the valence band is filled with electrons up to the edge, the valence band edge. So now there's no vacancies available, no orbitals available for metals or for electrons, so they cannot move anymore. So they're stuck there. So if they now want to move, you have to excite them over a forbidden zone. There is no states possible there. And then via the conduction band, this is what I call the conduction band, there you conduct electrons. And an intrinsic semiconductor, so non-doped, Fermi level is in the middle of the gap, even if there are no available electronic states for the electrons to be in. Then we go to N-type, and today I'll just focus on N-type semiconductor because it's more similar to a metal, because you have electrons and this is holes. So what you will have if you put donor atoms inside, so you have a crystal lattice, you put 10 to the 15 to 10 to the 19 atoms inside which have 1 electron more than the rest in the bulk of the material, you get doping. And then the Fermi level shifts towards the conduction band edge. And these donors are excited, the electrons are excited in the conduction band, and then you have a doped material. But the charge in this layer is much lower than in the metal. Metal is like 1 mole or something of charge compared to. So p-type is just the opposite. So the work functions are then also different. In this case, for N-type has a different work function than a p-type, which has the Fermi level lower than an intrinsic one. It's already half an hour. Okay. So what will happen now? If you have 2 metals, you put them into contact. So we have metal 1 with a small work function and metal 2 with a larger work function. So what happens now? We have clearly a difference in Fermi level. And if you now put them together, they sandwich, then what you will have is that electrons from metal 1 are transferred to metal 2. And equilibrium, Fermi levels are aligned. If you now use a voltmeter, basically you don't see a voltage difference because the Fermi levels are equal. But what you have is an interface potential, we call it the volta potential, because here you leave remaining charge, here is incomplete, here you leave positive charge behind because you remove electrons, and there you build up electrons. So you get a potential at the interface. You cannot measure the voltmeter, but you need a Kelvin probe for that, so you have to go very close at tunneling distance, and then based on that tunneling current you can estimate this potential at the interface. So this is 2 metals. So if we now take 2 metals and we put them into solution, remember this, or look at this, it's open, it's not short-circuited, so it's out of equilibrium. So what will first happen is metal 1 will get in equilibrium with the solution, and metal 2 will also get in equilibrium with the solution at the surface, because you also will have exchange between the Fermi level of the metal and the solution. So if you then put a voltmeter on, then the difference in potential is not the difference in work function anymore, because you get this electrolyte metal interface, which also has a potential. So you divide it. So the potential of metal 2 is larger than metal 1. So this is an oxidizing metal, this is a reducing metal. So if we now take copper and zinc, we can see we have a big difference between the copper and the zinc. So copper is more positive and the other one is more negative. And because these are all measured under standard conditions, all these redox potentials, we can say actually that, like in physics, that the standard redox potential is actually the Fermi level of your redox couple. because it's all about energy levels in this case. So this is again in contact, but if you just forget about all these interface effects, if you just look at the difference in work function, intuitively you see where the current will go. It's just from metal 1 to metal 2. And now, this is the magic of the galvanic cell. For me, it's kind of a magic thing. So what you will have, if you now close the circuit, so you short the two metals, electrons have to move to the other side. And what you will have is that here you have an excess of empty states, because normally these states are filled. And there you have an of empty states, and here an excess of filled states. And what actually happens is that you have here on the metal redox interface, let's say, redox couple interface, there was an initial equilibrium, but now you disturb this equilibrium. And what will happen is that the electrons will go in the empty states of the metal. And they pop in. It's a bit like the communicating vessels. One go in and one go out, because they have this driving force. You don't measure it with the voltmeter because the Fermi levels are aligned. But anyway, they move, so they have an inner built-in potential at both interfaces. And this for me is very nice. So in a galvanic cell, two electrochemical reactions are separated and connected through an external electrical circuit. So it's a spontaneous reaction. So if you want to see if it's spontaneous, you can just fill in the Nernst equations. So the Nernst relates the electrode potential, oxyred1, with the standard reduction potential and the activity. And then you can just do for both reactions and can rewrite it. And this reaction is spontaneous when the potential difference is larger than 0. This is what you would expect also intuitively based on work function. So the Gibbs free energy will be negative. But activity is a bit complicated because we don't really know often what is the activity of the solution. So the activity is related to the activity coefficient and the concentration. If you then rewrite everything, you can basically extract the activity part out of these equations, and you go from standard potential, which is based on activity, you go to the formal potential, and in the formal potential you have the activity part. And if you now are clever, you use concentration ranges in which the activity will not change too much. Basically, this will just become, this will vanish, and then this will become the standard potential. So it's a little trick electrochemists do. And yeah, based on our cell, we have a cartoon here. So we have a salt bridge in the middle to slow down the reactions, so they don't react instantly. Because what I forgot to mention here, this reaction here is more when you put them together instantly. And they will react like that spontaneously. But if you now separate them, this redox potential is actually converted. They call it now a cell potential, but in principle the same thing. So this one depends on so it's 1.1 volt. And this potential you can change with the concentration. So if you increase the copper concentration, so what will happen is that the reaction on the counter electrode will be kinetically much more favorable. And basically what happens is that Fermi levels will be shifted. So in the positive, the Fermi level will pull down. So you can really optimize this thing. So that's what people do. So now if we apply this to a zinc sulfate, copper and copper sulfate system, so what will happen? So just to summarize, so we have two different work functions, two different Fermi levels. When we connect them, go in equilibrium. And what we will have is that the zinc has empty states available and it wants to refill it because the interface is out of equilibrium. So what it will do, it will oxidize itself, it will like sacrifice itself to go to a lower energy state. And the copper will just take the electrons. And if you put something in the middle, you can do some work. So this is the principle of galvanic cell. So it's already very old, but I think the full physics, maybe it was probably this century. That took very long, probably. So we had very clever people, Helmholtz and Nernst, to figure it all out. So I have again Italy in the example, I'm sorry, but corrosion. So corrosion is a big issue. I read about it. I'm not a corrosion person myself, but it costs apparently like thousands of billions of dollars a year, because the nature wants to go to lower energy. And yeah, we had a very terrible accident in Italy where the bridge collapsed, and this was a corrosion effect. And this is it's very difficult, because if you have a beautiful boat and you don't maintain it, it will go back to dust like that. You cannot, the force of nature is extremely strong. So what you will have in this case, you have always an adsorbed layer of water on the surface, and oxygen diffusion is really fast. So you have easily tens, maybe 100 ppm of oxygen inside. And what will happen is that you get an electron, you get a galvanic cell basically. Oxygen takes up electrons, iron is oxidized, and it forms rust. And the problem with corrosion of iron is that the oxide quality is really crappy, because it's a porous oxide, so it doesn't protect the surface. If you have aluminium, aluminium is super reactive material. It's not stable in water even, but it passivates itself by high density oxide, so it's always perfect. And with iron, you don't have that. And this is one of the reasons. So a galvanic means that you get a locally enrichment of your oxygen and a depletion of oxygen. And because of the difference in concentration gradient, you can see from Nernst, is that you increase the cell potential, and then this thing only gets worse. So that was a problem. So you always need to paint. If you have some metal, you have to passivate it, protect it chemically to stop the galvanic cell. That's basically the principle of painting of metal. So now powering everyday life. I updated the slide. If you have this in the last one, because Tesla, they have apparently, I had first it was a power pack, but recently in July they have now a mega pack. So 3 megawatt hour of batteries, so a lot of batteries. And they can go up to 250 megawatt hour, so a lot of storage. Because, for example, in Belgium, we're in a nuclear reactor, so I was wondering, why do you put always the light on the street in the night? Nobody drives there, too many lights. But what they do is they have too much energy, and they just keep the lights on the highway, because otherwise they have to put down the nuclear reactor. So, and this is not possible, it has to keep running. So wouldn't it be wonderful if you can store it? It's the same as Tesla, the Powerwall at home. I'm just doing commercial, it's maybe too much, but I like the principle. If you have solar, in the night you don't have energy. So if you want to really be independent, you need to store your energy and use it in the night. This now is too expensive, I think 3-4 years. Then it becomes interesting, because solar cell price go down a lot. And if this go down, then also in Belgium with this new smart meter and everything, this is the way to do it well. A car now, 400 kilometers an hour. But what is more interesting for me is the distance than the speed. So they are working also at IMEC to go 700 kilometers on one tank of energy. That would be the ultimate. And then overnight you can sleep, and overnight you can hopefully charge it. So personal electronics, so everybody has laptops, it is full of batteries. Bikes is very fashion these days. But also miniature, so making batteries very small. You can see it on your finger even. And this is smart sensing. So if you have fruit, so I think it's acetylene comes out, you can see how ripe it is. And basically this will give an electron to your circuit and will be measured as a current. Or the resistance will change, and then you can see, oh, my pears are wonderful to eat, or too late, and it's also possible. So also for bio applications, so you can put it inside yourself, charging batteries by just moving, and then they can check everything of you if you put it on your phone. So this was quite interesting. Fuel cells is another example of a galvanic cell. So NASA is doing research on hydrogen fuel cell for spacecraft or aircraft. So that will be quite challenging, but imagine that, you charge your plane, go to the other side of the ocean, and come back. Yeah, that would be really nice. You also have hydrogen in the stick, so hydrogen gas. You can put it in and you can do a flashlight or something. Or domestic heating, they also already have it. Or portable fuel cells, so if your phone is empty, just plug it in and the hydrogen will do the rest. So, and then we have the fuel cell car. I like this principle better than the normal charging of car. This is hydrogen gas, you put it in, but the problem is it's too much small, you cannot keep it. So this is the principle of the fuel cell. So you put hydrogen in, it's oxidized, goes in external circuit, and the protons go via an exchange membrane to the other side, and the electrons react with oxygen to make water. So it's extremely clean. And yeah, you can just calculate, so the potential difference between the oxygen reduction and so the oxidation of water and the reduction, or the oxidation of hydrogen and the reduction of oxygen is almost 500 kilojoules per mole. So it's a very favorable reaction. So now it gets a little bit more complicated. So we have galvanic cells, and you can use this for patterning of structures. People have been doing this a lot. So what you do, you put a noble metal on a semiconductor surface, like silicon in this case. So you get this built-in potential between the silver and the silicon. Because the silver has a very low Fermi energy, so it's very stable, and you have silicon with a higher Fermi energy. So you have a driving force based on the difference in work function. So what happens now, if you put it in solution with peroxide, peroxide will oxidize the silver, and the silver so he has an empty state available, and he doesn't like that, he wants to be reduced. So what silver does, takes directly an electron from the valence band of silicon, and it's reduced. So silicon is oxidized in the process. So like aluminium, if you don't add an acid to it, the reaction just stops, because yeah, it's passivated. So what you need to do is, in this case, HF, not the most healthy acid, but it works very well. And just keep removing the oxidized surface, the oxide from the surface, and basically your particles are digging into the surface. And in this case, silver is so they write it all as reduction reactions. For me, it's not less convenient. I'll come back to that later. But silver is actually a catalyst, so it's just oxidized and directly reduced, so it's not consumed. So it's a catalyst. Yeah, so here you can see there was done a Dymec thing. So it's a cheap way. You just put silver on it, you etch it, and you have a high surface area structure. So here you can see on the right, so these particles, they completely dig in. And what actually is quite bizarre is that you can also make pillars, but then actually the openings, they stay behind, so the whole plate of gold is etched down. You can make pores, holes, so a very nice pattern of holes, or even make sheets. So people have been very creative, trying to do all kinds of things. This is an example of electrochemical etching, and we call this electroless redox etching. And electroless etching means there is no applied potential. So you just let the inner potential of the system do the work. So what actually happens, so now you have to, what I tried to explain you, the difference between chemical etching and electroless etching. So chemical etching is actually only occurring at the surface. So you have electrons and surface bonds, they react with your peroxide, and that's it. But in this case, you take an electron from the valence band, and an electron from the valence band is mobile. If you would apply a field, you would measure a current. And why is this thing mobile? So what you see is that, okay, you have the highest etching here at the interface, but if you go completely up the pillar, you also have some etching there. So these holes, they can diffuse as long as up to the diffusion length until they get annihilated. So what basically happens is that, I wrote it here for silver, so we don't write it as a reduction reaction, but we write it like this. So 4 silver plus goes to silver reduced plus a hole. And then silicon reacts with holes to silicon 4 plus. And the hole is not necessarily etching. So the hole only etches when it's localized in the surface bond. And the hole is actually an empty electron state. So if this one moves to the surface, then the surface is oxidized and then you etch it. If it doesn't go to the surface, it does not necessarily have to etch. So this is one of the problems, I think, of the system. They all do these nice patterns with noble metals. So your surface is completely contaminated with gold. And for silicon, it is not measured at least. For silicon, if you have, I think, one gold atom can already ruin your device, your transistor. So that's why this will never make it into device, Intel or something, this kind of processes, or Samsung, they will never accept it because it's cursing, let's say, if you use noble metals in semiconductor fabrication. It's difficult. So what I showed you before is metal-assisted etching, but you don't necessarily need a metal. If you just take a redox couple, like cerium 4 plus 3 plus, this one has a Fermi level which is even lower than that of indium phosphide, but also of gallium phosphide. So basically, electrons from the valence band can move there, and they reduce the cerium, and at the same time, it's easier to say a hole is injected. So this is called electroless etching. And this kind of mechanism, so you need, of course, the redox potential to be larger than the potential of the solid and the ion in solution. This kind of mechanism is very complicated because you have 6 holes, and each injected hole has a different kinetic constant. So if you really want to figure out, you need some good mathematics, I think. Yeah, you also form all kind of band gap states and so on. So, are you still okay? Not too tired? How long is your break usually? 5 minutes. So then I can take it a little bit slower. So now, we discussed galvanic systems. So a difference in Fermi level as a driving force. And now we go to the other case. So the electrolytic cell. So the galvanic cell, so just a summary. Current flow due to difference in electrochemical energy between 2 electrically connected electrodes. So you have spontaneous reaction, so it can make work. And it's very important for batteries, fuel cells, corrosion, one of the biggest issues, and etching. So the oxidizing agent is reduced at the cathode, so the negative electrode is the cathode, and the reducing agent is oxidized at the anode. The cathode is the positive electrode, means the electrons go there, so it's an... Actually, this is confusing, because I'm only used to electrolytic cells, electrochemical cells. In this case, the cathode is a negative electrode, and the anode is the positive electrode. And the cathode is the positive electrode because in this case, it just has a low Fermi level. So the electrons go there. So that's the difference. And here, this is an automatic, so you always put where the electrons go. This is the cathode, and where the electrons go away is the anode. So here is the same applied potential, but then the negative, you put the electrons on the surface, and here the positive electrode, you take them away from the surface. So the potential is defined with respect to a known reference electrode. So as I told you before with the neuron, so if you want to probe really what's going on at your electrode, you always need a reference. And you then in this case you have a 3 electrode setup, So we have the working electrode, so this is the one, a probe, let's say. We have a reference, so the reference can be the standard hydrogen electrode, so I forgot to tell you this, but this is the defined, so this is defined as the zero voltage reaction. And actually it has a work function of 4.44 approximately. So, but it's more common, in the past they use a lot these kind of electrodes, because then you have hydrogen gas inside your electrode. But what we now use is a silver chloride. And one I like to use the calomel electrode, but now it's forbidden because there's mercury inside. So I always gave everything, because these have a fixed potential, and this is an easy electrode because it's based on a solid, and you only have to control the chloride concentration, the activity in this case. And then you just use a saturated KCl and it works. So they have a fixed potential, 0.244 versus standard hydrogen. So this is a bit more positive. And the silver chloride, 0.2, let's say. So this is our reference. So what we're now going to do is to vary the Fermi energy with respect to this reference. This is what we do. And then you always have a control. And this is then called the auxiliary electrode or the counter electrode. And that's basically where you dump your electrons, because you want to get rid of your electrons and they go to the counter electrode. It's always good to have counter electrode 5 times larger than the working electrode, so you don't have kinetic limitations because of size. Because imagine if you have a working electrode like this and a counter electrode like this, yeah, you don't get the electrons out. So you have a lot of resistance. So in this case, this is the only thing you have to check. So in this kind of setup, it can teach you a lot of things. So now it's 1 hour. I will stop here. This is a potential window of water. And then we go to metals, and then semiconductors. So yeah, so 10 minutes.